King's College London. He will talk about type 1 and type 2 supersymmetric backgrounds.
I would like to thank the organizers for their kind invitation and the organization of this wonderful conference. I'll talk about supersymmetric solutions of type 1 and type 2 supersymmetric backgrounds. This is work based in collaboration with Wolf Brown, who is sitting over there, Dietrich Rost, Jan Gutowski, and my students Philip Lochman and Peter Sloan. I will begin with some general remarks about the structure of the King-Spinor equations in type 1 and type 2 supergravities. And then I'll explain how one can go about to find all supersymmetric backgrounds in type 1 supergravities, at least the structure of their geometries. And then I'll continue, and then I'll describe what's the status in type 2b supergravity theory, and then I'll give you my conclusions. Now, the King-Spinor equations are the vanishing variations of the fermions of the supergravity theories, and for one of the fermions, of course, is the Gravitino, and the King-Spinor equation is the parallel transport equation. But the first part is the Levi-Civita connection, but it has an extra part that depends on the fluxes of the supergravity theories, which it has an expansion in symmetric products in gamma matrices of higher and higher order. So this is not quite what one expects from, let's say, in Riemannian geometry. The other King-Spinor equations are the vanishing variations of the other fermions of the theory, and these are typically of algebraic type. And the task that I have set of ourselves is to see whether one can solve the King-Spinor equations without making any assumptions on the metric or the fluxes. So completely generically, without any answers or any other assumptions. One has to understand a little bit the general structure of these equations and why, and what is the real reason why it is so complicated to have completely general solutions. And if one has to solve a parallel transport equation, the most natural object to look at is the holonomy. And the holonomy of the supercovariant connection of 11-dimensional supergravity and 2p supergravity for generic backgrounds is inside SL32R. This can easily be seen by computing the commutator of two supercovariant derivatives and see that it takes values in the Lie algebra of SL32R. Now, if you have one background with L parallel spinors, and typically the number of killing is a bit less than the number of parallel because some of the parallel might not solve the algebraic, let's say, King-Spinor equations, then the holonomy of the supercovariant connection is inside the stability subgroup of your parallel spinors inside SL32R, and the stability subgroup is SL32R minus L. L is the number of parallel spinors, semi-direct L copies of R32 minus L. The main observation here is that for any L apart perhaps from L equal 32, this is a non-trivial stability subgroup. One of the consequences of this is that on this, at least on the grounds of holonomy, there might be supersymmetric backgrounds for any L. So for type 2 supergravities, one can have backgrounds with 1 supersymmetry, 2, 3, up to 32, with no restriction whatsoever, at least a priori. Actually, supersymmetry algebra arguments reach the same conclusion. However, this is not the case, as I'll explain a bit later. The other ingredient of King-Spinor equations is the gauge symmetry. Well, gauge symmetry of King-Spinor equations are those transformations that leave the form of the King-Spinor equations invariant. So, with a little bit of work, one can see that in 11-dimensional supergravity, the relevant group is spin 10,1, into B is spin 9,1 times U1, and for type 1 is spin 9,1. Now, if one has a gauge transformation of this type, it's completely natural when you have a classification problem of this type to identify configurations that are related by a gauge transformation. But then immediately you can see the problem, that the gauge groups like spin 10,1 are much, much smaller than the holonomy groups. And so if you have, let's say, so there are many more geometric types that can occur for a given number of Killing spinors. To give you an indication how small the gauge groups are, if you have, let's say, two spinors, epsilon 1 and epsilon 2, they have a non-trivial isotropy group inside the SL32R, but inside the gauge group, in fact, the isotropy group is 1. Of course, in type 1 supergravity, the thing is much simpler. The gauge group and the holonomy group coincide, and this is actually a great simplification. To continue this comparison between holonomy and gauge symmetry, let's take the situation for one spinor. Now, for one spinor in 11 dimensions, this is a Majorana spinor, the isotropy group is SL31, R, semi-direct R31, but the isotropy group in the gauge group are basically, there are two possibilities. There's a generic orbit with stability as U5, and there is a special orbit with stability spin 7 semi-direct R9. In 2B, of course, the isotropy in the SL32R is the same, but in the gauge group has there are three different types of orbits. One spin 7 semi-direct R8, SU4 semi-direct R8, and G2, which is the generic orbit. So you see that for an equals 1 supersymmetry, one has two geometric types for one supersymmetry, and in 2B at least three geometric types. In type 1, the spin 9,1 has a single open orbit in the Majorana value representation with isotropy group spin 7 semi-direct R8. Now if you continue this comparison and you go to the other end for 31 spinors, then you can see still you get some non-trivial isotropy group in SL32R, but the stability subgroup in the gauge group is 1. So there are several geometrical types for the same number of Killing spinors, and it would have been very nice if somehow we had a way to enhance the gauge group. In that case, it would have somehow led to less possibilities. But at the moment, I'll stick to the gauge groups I just mentioned here. Now, if one puts these ingredients together, one can make a very effective method to attack this problem, i.e. to try to solve the Killing spinor equations in general. Now, the idea, first of all, is to use the gauge symmetry to orient your Killing spinors along particular directions. And in fact, if you have too many Killing spinors, then probably it's better to orient their normals. It's much more convenient. And then this procedure is quite effective for very small or very large number of supersymmetries. Another piece of convenient notation is to use this writing of spinor tensor forms that goes back to Cartan. And eventually one can use an oscillator basis in the space of spinors and the linearity of the Killing spinor equations to extract the geometric information. Okay, let's start now with the Gravitino Killing spinor equation of type 1 supergravities. Now, this is a parallel transport equation of a metric connection with torsion. Now, for generic backgrounds, as I've mentioned, the holonomy is inside is spin 9,1. Now, if one has one parallel spinors, one can work the integrability condition, and then the curvature of the connection, the Hutton connection with torsion hitting the spinor is equal to 0. Now, this implies that either if the parallel spinors have stability subgroup 1, then necessarily the curvature must vanish. Therefore, the space-time must be parallelizable, and then if in addition the free form is closed, then it's a group manifold. All group manifolds, all Lorentzian group manifolds have been classified. So there's a actually all the parallelizable up to dimension 10 Lorentzian manifolds have been classified. So I guess we have a complete list of all the possibilities. On the other hand, if the parallel spirals have have a non-trivial isotropic group, so they are singlets, well, then we have to find all possible subgroups of spin 9,1, and they are singlets. And then the holonomy, of course, of this connection over here, it has to be inside the stability subgroup of the parallel spinors. And here's the full list. So this list on the left-hand side is the number of singlets that occur in the Majorana value representation of spin 9,1. One can have 1, 2, 3, 4, 5, 6, but the 7 entry is missing. And there are two types of possibilities having two spinors. And then one goes up to 8, and then the possibilities between 8 and 16 are missing. There is a desert there. If you have 9 spinors, then necessarily their stability subgroup is 1. There are two types of stability subgroups. These are non-compact, and these are compact. And it turns out the geometries of the associated backgrounds are completely different. What I have highlighted in red are what is sort of different from what might have been expected from the Berger classification list. You see, one can recognize a lot of Berger type of groups here on the list, but there is an isotropy factor in these cases because of the Lorentzian nature of the problem. Moreover, there are two exotic cases that appear over here. One has 5 parallel spinors and the other has 6. And this case here perhaps is not that surprising because it's associated with PP waves in flat space. But also the fundamental string is in this particular entry. Now in this list over here are the singlets, and represent spinors but written in form notation. So I'll just say a few words about this notation. One can identify the Majorana value representation of spin 9,1 as a real subspace of the even forms on C5, using this reality condition, which some conventions can be chosen like this. Now, in this notation, the spinor 1 is complex vile, and it has 2 Majorana components. One is this and one is that. So you see the real spinors are multiforms. So, and then this notation E1, 2, 3, 4, 5 means wedging the basis of C5 in appropriate way. So if we go back, one can now recognize the various entries here as the spinors. Now let me go to the Dilatino clean spinor equation. One can assume that has a solution of the Gravitino clean spinor equation. And it might be the case that not all parallel spinors are killing, because some of them simply do not solve the Dilatino clean spinor equation. So the solution of the Dilatino clean spinor equation is going to be a linear combination of the parallel spinors. If that's the case, it's rather complicated to solve because one can have lots of possibilities to consider, and then when you substitute in the Dilatino clean spinor equation, one might not be able to solve the equation. So the idea is again to use gauge symmetry, and it seems after a bit of thought that the right gauge symmetry to use is this group sigma p here. Now sigma, if one denotes with p the plane that spans all the parallel spinors, and take now the transformations in spin 9,1 that preserve the plane, and one modes out with the stability the isotropic group of the parallel spinors, because in any case this acts with the identity on P. This is the right gauge group to use. It turns out if one uses this, then one can find all the possible Killing spinors in all cases and solve also this Dilatino Killing spinor equation. In fact, if the number of Killing spinors is more than half the parallel, then it's much more convenient to use this group here to choose the normals to the Killing spinors. And here is the full list of possibilities. So now in the left column, it's again the number of parallel spinors in each case. They are the isotropic groups in spin 9,1. and here is the list of all sigma p groups. Now, looking at the sigma p groups associated with the non-compact isotropy groups, one can immediately realize that perhaps these are kind of groups that might appear in a two-dimensional supergravity theory. The first part is just spin 1, 1, and the second, the compact part, it might be just an R symmetry. You see, if you look now at the entries 5 and 6, that indicates that might be supergravity theories in two dimensions with 5 and 6 supersymmetries. And as far as I know, these have not been constructed. And they have appropriate R symmetries sp2 and SU4. Now, in the compact cases, the corresponding supergravity theories in higher dimension. The G2 case is the supergravity theory 3-dimensional, the SU4 is 4, the SU2 is 6, as might have been expected, in fact. And here is the list of possibilities. After doing the hard work and finding all the solutions, these are the possibilities that really occur. So here, again, on the left is the number of parallel spinors in each case. Now here is the list of the sigma groups, and here are the possibilities that occur. Of course, if we have one spinor, then that's one possibility. But then, of course, if we go, let's say, to other cases, then, for example, in the sp2 case, there are 3 potential parallel spinors, and there can be 3, 2, or 1 killing. Now, what appears inside the brackets is a number of different geometries that one gets for a given n. So for all the non-compact cases, there is one single case for every entry. But for the compact cases, the situation is much more complicated. For example, if one takes this case here, then which corresponds to SU3, then there are 2 different types of geometries for n equals 2. Although one has still 4 parallel spinors. And so on. In the most complicated case, corresponds to SU2, for n equals 4, there are 6 different possibilities. Now the cases, well, before I do that, let's go also to this spin 9, 1 case. It turns out there are no backgrounds with less than 8, and then there are backgrounds with 8, 10, 12, 14, and of course 16, which is Minkowski space-time. The backgrounds that, the cases that I indicated in red are the cases where all parallel are killing. And there is one case here that I highlighted with blue, and this case actually is what one call Preoni case. That means under a very mild assumption like DH vanishes, this case is excluded. Let me say something about the geometry. I certainly wouldn't have the time to give a detailed description of their geometries. In fact, we know all the geometries in all cases, but there are some distinct kind of features between the compact and the non-compact cases. In the non-compact case, in all the cases where the isotropy group of the spinors is non-compact, the space-time admits a single null parallel one form. Of course, admits other forms as well, but let's concentrate on the one forms. In the compact cases, the G2 case has 3 and 1 is time-like. In the SU4 admits 4 and 1 is time-like, and SU2 admits 6 and 1 is time-like. And this is a typical kind of symmetry algebras of the space-time that they occur. In fact, these algebras have been classified, so we know all of them up to dimension 10 and more. Now let's talk a little bit about the geometry, the rest of the geometry. For the non-compact cases, the space-time admits what's called a Cauchy-Riemann type of structure, which depends on what kind of maximal compact group K one has. And H is determined, most of it is determined in terms of the geometry and the various invariant fundamental forms that these manifolds admit. In the compact case, the space-time is a principal bundle equipped with a natural connection, lambda, and the fiber are the orbits of the vector fields associated with these forms. And the base space admits a K type of structure compatible with a connection with skew symmetric torsion. And all H is determined in terms of the geometry. Knowing all the conditions, of course, that occur, then one can start thinking about the existence of solutions under various assumptions. Let's take the SU4 case here. Then, by the assumption the holonomy of the hatted connection is in SU4, semi-direct array, then one knows a priori what are the parallel forms. They are all null, and there is in one form, there is a 3 form and 2 5 forms. The 3 form is associated with the Hermitian form, and the 2 5 forms are associated with the real and imaginary parts of the 4,0 form, the SU4 4,0 form. Now, however one assumes the field equations, the closure of H, and this assumption over there, then one can see, using the various Bianchis, that actually one has even more parallel forms on the manifold. Now, these parallel forms do not vanish for the cases where the number of killing are less than the number of parallel. So there are two possibilities. If you want the existence of backgrounds with killing less than parallel, then one has to reduce the holonomy to a subgroup of the isotropy. If one insists that the holonomy is equal to the isotropy, then the Gravitino killing spinor equations imply the Dilatino one, and all parallel are killing. So this is the kind of games that one can play now, knowing the conditions in all cases. Now this is the summary of what is happening in 2B. In 2B we know there are 4 types of difference geometries that occur for n equals 1, associated with stability subgroups spin 7, SU2, and G2. For n equals 31, the supersymmetry enhances to n equals 32. So there are no backgrounds with 31 supersymmetries. The n equals 32 backgrounds are known. It is Minkowski, ADS, and the plane wave. And recently there's been a paper by Jose Figueroa Faro, Hackett-Jones, and Chopoulos that they show that backgrounds with more than 24 supersymmetries are homogeneous. Now we have some early indications that say that actually backgrounds more than 28 supersymmetries are actually maximally supersymmetric, but we haven't confirmed this as yet. Now, of course, this is the list according to not making any assumptions about special structure like special invariant spinors or special isometries of the space-time. In fact, one might argue that the best known solutions have all these properties. But then I haven't mentioned because I haven't quite. I look at the thing from a different perspective. Now let's see how one can go about proving that n equals 31 implies n equals 32. Now if you have 31 killing spinors, then they span hyperplanes in the space of spinors. So one can use the gauge symmetry to choose the normal. And then after a bit of work, one can see that the representatives of the normal can be given by these expressions here, where f and g are space-time functions, as is h and k. Now, choosing this normal, one chooses the killing spinors orthogonal to that normal and substitutes in the algebraic killing spinor equation into B. And then after a bit of work, one realizes that the 1 form and the 3 form field strengths vanish. If this happens, then the remaining killing spinor equations become linear over the complex numbers, and they admit always even number of supersymmetries. So n equals 31 implies n equals 32, and there are no backgrounds with 31 supersymmetries. Now this is also the case for 2A supergravity, and this has been also extended for 11-dimensional supergravity as well, but the proof here is a little bit more intricate and uses the field equations of 11-dimensional supergravity and the Bianchi identity for the 3 form to kill the extra components which is along the holonomy R31 that associated with these backgrounds. How much time I have? There has been some recent interest in backgrounds for which the 3 form field strength and the 1 form field strength vanish. Now these backgrounds automatically have n equals 2 supersymmetry, and one can go around and trying to find what are the generic geometries for these backgrounds. And now these are special cases of n equals 1. And here is what really is happening. Here are the stability subgroups of the spinors, And here is the form of the killing spinors in every case. And there are two cases that occur, two different types of geometries that occur for the same isotropy group. The generic and the pure. Now the generic, with generic I mean that f, g, h, and k are generic functions of the space-time. Now the pure case is the killing spinor actually is a pure spinor. And they have distinct properties. In the first case, the spin 7, actually this space-time admits a parallel null one form, and so it's a pp wave propagating on a holonomy spin 7 manifold. In the generic case, one still has a parallel killing null vector which has a trivial twist. In the pure case, there is also a killing vector field, but the twist is non-trivial. And in the G2 case, there are three different directions. One is time-like killing direction, and there are two more directions where the associated one forms are closed. Moreover, one can say, what is the geometry now transverse to these directions? In the first case, I already mentioned that just as holonomy spin 7 manifolds. In the generic case, the Craig-Harvella classes are completely determined in terms of the functions that appear in the killing spinor. In the pure case, one gets the W1 and W2 to vanish, which indicates that there is an either double complex structure on the transverse space to the light cone, and there is a relation between the new forms associated with the Hermitian form and the 4,0 form. And the last case, perhaps, is the most interesting one, is where the 7 transverse space admits a co-symplectic G2 structure. Now, G2 structures have appeared before in supergravity backgrounds, but they are much stronger than what appears here. I mean, typically you get a nearly parallel structure, but this is just co-symplectic. It's much, much weaker. It turns out that if you lift the ADS5 black holes to be supergravity, then one lands in the pure case here, in the pure SU4 case here. And the LLM solution admits a co-symplectic G2 structure belongs to this class. So, here are my conclusions. The clean spinor equations of type 1 supergravities have been solved in all cases, and the conditions that are imposed on the geometry by these backgrounds by supersymmetry have been found. Much progress has been done for 2b. The clean spinor equations have been solved for n equals 1, and in the case for p equals 0 for n equals 2, and the geometry of the backgrounds have been understood. 2b backgrounds with 31 supersymmetries are actually maximal supersymmetric. The maximal supersymmetric backgrounds have been classified. Backgrounds with more than 24 supersymmetries are homogeneous, and it's likely that backgrounds with more than 28 are actually maximal supersymmetric. And here I leave you with a list of the group theoretic data that have assisted in the classification of supersymmetric or geometric types in type 1 supergravity. Thank you.
Okay, questions there?
I would like to comment that this table of isotropy groups follows from a trivial dimensional reduction from the analogous table for null-killing spinors in 11 dimensions that was first given by Marco Carillia and I. I would also like to comment that your classification procedure there was a prior independent formulation of it that I called refined G-structure classification.
Well, I mean, I don't claim that these groups have not appeared before. The groups were known, but as far as I know, this list that appears here is a new list, and also the sigma p, which were also critical in solving the Dilatino killing spinor equation. And moreover, there might be, I agree with you, there might be much better ways of solving the killing spinor equations from the one that I have just proposed, but we used the method I just said to solve the killing spinor equations.
Greg?
Have you looked at the killing spinor equations for the ghosts of the Gravitino? I ask because there's a little puzzle in writing down the Gravitino partition function in supergravity.
Well, I just used the standard Killing-Spinor equations as arise from the supersymmetry variations of the fermions of supergravity theories.
Yeah, but did you also look at the ghosts of the gravitino?
The
They
ghost,
couple to a modified Dirac operator, which is not, which
No,
doesn't obviously have the same form, well, whose zero modes are not obviously the same as the zero modes when you have of the gravitino. And that's important because ghosts are commuting for the gravitino, and they can lead to divergences in the one-loop partition function for supergravity.
well, I just used the supersymmetry variations that John Schwarz has found in his paper for the 2B supergravity, and for the type 1 supergravity, I just gave you the parallel transport equation that I use.
I understand that, but I'm just saying that there's a further analysis that would be very interesting to do.
Okay.
More questions? Well, if not, we can thank Georgios again.